All right, hi everyone. Thank you for coming to the workshop today. My name is Maggie, and I'm gonna be hosting the circuit analysis workshop. So before we start, who here is an EE? Wow, there's 3 of us, 4 of us. I'm an EE as well. So, anyone CE? Yeah. Oh wow, there's so many. Okay, this is really good because yeah, anyways. And then any other people that aren't like other majors, like mechanical? Oh, cool, cool. Let's go. Arrow. Oh, arrow, 1 arrow. Others, etc. I don't know who else. What are you? Just a random major. Oh, okay, yeah. All right, so today we're gonna be doing we're gonna learn the very basics of like circuit analysis. So like stuff you would learn in like the first class of ECE. And we're also going to be doing some simulations. So if you don't have like a simulation tool like LT-Spice, Multisim, P-Spice, like it's totally fine. I'm gonna simulate it. So hopefully you guys can just watch along. And then we're also gonna be designing a few very basic circuits too. So hopefully we have time. We're gonna do like some problems as well. So hopefully you guys have a computer with the software. If not, it's all good. Or a pencil or an iPad with tablet, whatever. Right? Oh, you can't even see me in this, whatever. Hello, Zoom. Oh, someone left. Okay, just kidding. All right. Okay, so we're gonna I think there's 6 sections that I like split them up. So right now we're gonna be learning like the very basics of electronics, right? So what is electricity? Electricity is basically energy, and you can think of it as like oh, that's another slide. Sorry. It's just energy that is powering a lot of our stuff. So like this projector is, powering our slides. Your phones have power, the outlets, they're all power, If we don't have power today, like we'll be watching this on my piece of paper, we have a piece of paper and like the chalk or what is not chalkboard, the blackboard and like candles and everything. So can somebody name me a few like ways that we generate power today? Yeah, solar. Solar is pretty cool. Yeah.
Wind turbine.
Yeah, wind. Yeah, that too. Yeah. No. Yeah. Yeah. So those are like a lot. Oh, yes. Oh, thermal. Yeah. So those are like a lot of the cool stuff. I know for when I'm doing the project right now for my project, we only use solar so far. I don't think we use any other like way of powering besides our power supplies. So yeah, our solar is pretty cool, and it's very new with EV cars and everything. So yeah, that's the point I was gonna say. So basically what electricity is just electrons going inside the wire. And you gotta remember that electrons, there's like voltage and current, and you're gonna see like how the electrons move when I explain it in the next few slides. All right, so why do we use electricity? It's magic, right? Like I said earlier, if we didn't have electricity, we would be using like candles and everything. And so it's just cool stuff. And why do we use electricity in different applications like robotics? So this is the Hyperloop like soccer bot car. And if you guys are in the robotics club, they actually host a soccer bot competition each year. And this is one of the cars from Hyperloop that we designed. Everything on here is like electronics, right? You see all the wires, cables, coding, everything. So that's pretty cool. It's also used in vehicles. So when you drive, your Bluetooth, that's like electronics. spacecraft. So all the drones and the what's it called? The antennas in the sky, you know, when they shoot it up, satellites. What is the craft? The little like the rovers, you know, that's all electronics. City planning, you know, the street lamps. Computing is like what you guys do, or the CEs do, you know, computer engineering. You guys work on like the CPUs, the GPUs, that all that type of RAM, ROM stuff, right? So the first part you guys need to know about electronics is current. So what is current? Current is basically the rate of change in charge. Charge is the electrons, right? So when you see the equation, the D and then slash dt, that is derivative or change of something, right? And the measurement of current is amps or ampere, but you shorten to amp. And then when you like write it in your paper, your assignments, you can just put A, right? And high current, meaning that when there's a lot of currents, like a large value is like 3 amps. That's like a lot. And the more current there is, the faster the electrons are moving in the wire, basically. And when you have higher current, that means that the temperature also heats up. So like you're think of it as like water going through a pipe, right? If there's a little bit of water, your faucet is like dripping slowly, and there's not a lot of water going through, then you know the water is just like dripping. There's not much. But if you put like way too much, you like destroy, you know, just like push hella pressure, then it's gonna like explode or something, right? Your pipe is gonna explode. So you could think of it the same way. And 1 amp is actually enough to kill you. Your body itself is a resistor. So it's like a load. So if you touch, you know, if you take a fork and you plug it into the outlet, it's going to discharge through your body because the current is going to go through your body. And the reason why you die is because it goes through your heart. And then it like burns your heart or something. I don't know. I'm not a bio or, you know. But there's different type of current like tolerance, so like limits. So we could think of like Arduinos. Anyone use Arduinos here? Right? Oh wow, yeah, okay, cool. So Arduinos actually have a very low limit, current limit. So I guess it's considered 5 milliamps to 50 milliamps is considered low. And what high current is like motors, solenoids, those take around like, I guess 0.5 to 3 amps. The Raspberry Pi uses 3 amps to power up. So that's the higher, like these high current like devices, like a motor or like your microwave. Has anyone, well, when I was growing up, I kind of lived in a small house. So when I ever used the microwave and the toaster oven at the same time, my house, like the electricity would turn off. So we had to go outside and like flick it up, you know? So the reason why, it's because those like electronics, they use something called transformer, which converts power up, you know, from low to like high, which uses a lot, and transformers use a lot of current. So that's why you can't really use it two at the same time, because yeah, too much current. Oh, and a very important thing is that conventional current flows from positive to negative. And this is very important when you do circuit analysis. Like, remember this. Current positive to negative, right? So it goes out of the positive into the negative. All right, so we have voltage. Oh, okay. So voltage is basically I would say, opposite of current. Earlier we said that the electrons in the wire are moving, right? But what actually pushes it is actually the voltage. So voltage is what like pushes. How I think of it is current is just standing there, right? It's just here. but then the voltage, you have to, it's like pushing it or like punching it so that it like goes. Without voltage, there's no current, basically. Right? Yeah, no current. And then there's two forms of voltage. There is potential voltage, which is when you get like the difference between 2 points. So if I were to, you guys know what a multimeter is? Right? So a multimeter, it just basically helps you measure the value of the voltage across something. So if I were to put the voltage multimeter like here and here, then I would just measure at this specific, this load right here, right? Whatever voltage is across that load. And there's also polarity when it comes to voltage. So it's very important to place your plus and minus correctly. So let's say if this battery was 5 volts, right? And I put the red probe over here, and then the negative probe over here. What would be the voltage across this light? Yeah, whatever the drop is. And let's say if I put the negative probe on the top and the positive probe over here, what would the value be? Yeah, so it would be negative. So if this was, let's say this is like very ideal, right? So there's no voltage lost or anything. If this is a 5-volt battery, if you plug it like this right here, I'm kind of short, so if I was taller, this would be a lot better. But if I have my positive up there, my negative here, then it would be 5 volts. But if I swap the polarity of my multimeter, then it will give us negative 5 volts, right? And then there's something called node voltage, which is you have a reference point, right? And so I don't know who put it on the sheet, but they asked what happens when you don't have a ground, right? So this circuit doesn't really tell you where the ground is, where it is, right? So wherever you see the negative, you kind of just think of that as ground, and then you would put the ground like there, and then normally the ground is like your reference point. So wherever you put the reference point, you can probe anywhere on the circuit and it will be the difference between that reference point and, I guess in this case, it's ground to wherever that point is. And we'll do more examples of that when we do some practices. All right. Oh, perfect. Ground. So what is ground? What is ground? When I say ground, what do you guys think of? The ground, right? Yeah, so ground is ground. And a cool story, well, it's not that cool, but when I was building my what's it called, my koi pond with my dad, we needed to bring the electricity for the pump from our house all the way to like the backyard, right? And so when we connected the wire, we brought the wire, whatever, and then the outlet that we needed to plug in the stuff, there was 3 pins. There was plus, minus, and then a green one, which is ground. And so how he connected ground to ground, like in the real life, was he just took a wire, cut it both sides, like strip it off. He wired it to the outlet, and then he just stuck it to the ground and like covered it with dirt. So that's ground, right? And another thing is that people like electricians, if they touch like an outlet that puts a lot of voltage or current go through their body, if it touches, if your feet is connected to the ground, like if I'm just standing here with no shoes or anything, it will discharge from wherever I'm touching it all the way to the ground, right? So that's why a lot of electricians, they wear like big rubber boots, so then they don't discharge on the ground. So that's just safety, I guess. And a good point is that ground is just used as a reference point. So earlier I explained that if your circuit doesn't have ground, you kind of just imagine the ground to being there, right? And that's how simulation tools like LT-Spice, P-Spice, Multisim, they don't allow you to run anything unless you have the reference ground. Oh, and ground zero. And now resistance. What do we think of resistance? Like what do we think of? Not looking at this picture. Like when you hear resistance, it's just like you're resisting something, right? Like someone's holding you back to like fight or something. So resistance it restricts the flow of current. So just like me, if I want to fight Brian right now, you know, someone's holding me back, right? That's just the same thing. Electronics, it comes in a form of resistors. And what do you think it's in this resistor? Anyone know?
Carbon filament.
I actually don't know. But I just know that it's like it's just filled with like coils of wire, like it's just wires together. So you know the what's it called? When you draw the resistor, it's like line and then like that. So that's why it's like that. It's because it's just like wires in that area. Because if I'm walking from here to here, if I go in a straight line, obviously it's gonna take me like really quick compared to if I were to like, you know, it takes me forever to get to that point, which is like the resistor. If I'm going side to side, that's like resisting the time that I'm getting from point A to point B, right? All right, so the higher the resistance, the less current, which is kind of what I explained. And this goes to Ohm's law. Everyone know Ohm's law? Everyone should memorize Ohm's law. It doesn't matter what major you are, you have to memorize Ohm's law just because it's very fundamental, especially for EEs. Like this is the first question they ask you at interviews, and if you don't know it, that's how they determine, right? So V is voltage, I is current, R is resistance. So they kind of go hand in hand together, right? So we could say like this one, the higher the resistance, the lower the current is, right? It's just, yeah, it'll go in more detail. Fun fact. What is the human resistance value? Oh, it's also in ohms, by the way. So ohms, but what is the human body resistance value? Anyone? Yes? 100 mega ohms. I think that's too high. But I think the average is like 10K to 10 mega ohms. And it depends on if your skin is dry. So go dry skin. But just think of it as like if you wash your hands and you touch the outlet or like of, you know, something of that, your resistance value is a lot lower, meaning more current is flowing through your body, right? It's like when you put like a toaster in your bathtub, you know, that it's the same idea basically, right? And don't think that electronics is like death, you know. I've been here for 4 years, so I'm still alive, you know, so it's all good. It's cool, you know. You have to live life like exciting, you know. So. All right. So we just learned a few basics of like electronics. Now I'm going to show you a few circuit components. So earlier we just saw a resistor, but not really. Now you see what it looks like. And I'm pretty sure everyone, if you go to the 5th floor, you can see it. And resistors are used to protect from short circuits. So when you have a battery, let's say everyone know what a LiPo battery is? Yeah, no? Okay, so for those who don't know what a LiPo battery is, this right here is a LiPo battery. It's very powerful and the discharge rate is very high, right? So another fun story. When you use these LiPo batteries, you have to be very careful. If short circuiting is when you put the positive and the negative together without any load or resistance, right? Meaning 100% of that current is going back together, like it's in the same loop, right? So the funny story is that when I was at work, when I was interning like 2 years ago, the intern was an aerospace engineer, and when he was working with the LiPo battery, there's a plus and a minus, and he cut the wire where the connection is, which is not very ideal. You shouldn't do that, but he did it. And this battery was 24 volts, which is very high, very, very big. So the one that you just saw, that was 16 volts, like max. but the one we had was 24 volts, like minimum, or like not minimum, but like 24 volts, like average, right? And he shorted it and it blew up in his hand. And then he got like a 2nd-degree burn. He had to go to the hospital and everything. So LiPo batteries are pretty dangerous, you know. Take some class or training on them because they're actually very dangerous. But it blew up in his hand. And again, you know, you gotta live life fun. So it was a cool learning experience for him, right? So yeah, resistors are used to protect from all that short circuiting type of thing, right? Current control. Again, the amount of the resistor value that you choose limits the amount of current going through. Voltage regulation, you can actually, like, you guys saw the Ohm's law equation. However you change the resistor, it changes the current, which changes the voltage, right? It's all in a cycle, a 3-loop cycle. And you could use it to redirect signals. So has anyone heard of pull up or pull down resistor? Right? All right, that's cool. So what they do is that, let's say if you have a signal and you want it to pull down to ground, because if you put it, so you put a resistor to ground, that's just basically taking the signal straight to ground. And you can do that with the positive too. So you can take a resistor and put it to, like, pull it up from a low voltage to a high voltage, or vice versa. You use it, you can, what's the most common time to use it? Probably in a push button, right? Yeah. All right. Somebody also wanted to learn about capacitors. So capacitors are very cool because what they do is that they store energy. They basically just store energy. If that's an interview question, if anyone asks you, it's just a component that stores energy, right? Oh. All right. It's I put this because it similar to a battery, as you know, it's storing the power, the voltages and the energy inside that, like, bin. And then when you turn off the battery, it discharges. So you can think of it as, if I'm doing like the water analogy, you're putting water into a bucket. And then when you turn off that, like, power source, like the water source, you can use that bucket to power something else. Like you can use it to dump it somewhere, like your plants or something, not directly from the water faucet to, like, the plant, right? So super caps are very big because, I mean, super caps. So, you know, they're very large in storage, and they also discharge very high, meaning that the current that is going to discharge is just really high. And if you over voltage, if you're like, you know, bucket, the same bucket analogy, if you put too much water in it, it's gonna overflow. But in this case, the capacitor, they just blow up, right? And when are you gonna use capacitors? Capacitors are very common to reduce noise. And how it works is when you have a signal, the, like, extra energy that the signal is producing will go to the capacitor, and then, you know, it will discharge. Time sequencing, you can use it to, like, change the timing of the circuit, especially in like 555 timers. And I believe we will learn that in the next workshop, where you actually will build your own, like, circuits. And oh, before I start, this is basically him over voltaging it for you guys to see. Oh, that's fun. All right, he's turning it on. Oh, that's Yash, right? Yeah. So wait, no, you were in the video, right?
Oh, yeah.
Yeah. So that's what happened. Imagine if you didn't have that top, all the, like, particles would fly, right? Oh, it did? Oh. So yeah, just be careful. You could also blow LED lights, but I don't have the image of that, but. All right, inductors. So what are inductors? Inductors are basically the same thing where it stores energy, but this time in an electric field, right? Let's see. Oh, I'm not gonna go through that yet. So does anyone know the right hand rule? No? Yeah, so it's in physics 2, you should have learned like magnetic field and everything, right? Electric field. And so let's imagine the wire as like I'm facing it this way. So Pinocchio's nose from me looking straight out, right? So your hand, what it is this is gonna, their thumb is going to be the direction of the current, right? So current is going through the wire this way, right? There's a wire this way, you know? So the direction of the current is your thumb. And when you curl it together like this, that's the magnetic field, right? Yeah, magnetic field. That's around it. So that magnetic field actually is the reason why you can do like, what's it called? Wireless charging, because all that energy is, it's energy, the magnetic field, right? Some common inductors are in motors, brushless motors. If you look up the motor, the inside, you can see a lot of coils. That's the inductor. Microwave, I believe a lot of people hear that, but microwave is a really big, large inductor. Light bulbs are inductors, solenoids, wireless charging, like I said earlier. So this right here is when I did my project. So what I did here was we tried to put a 12-volt input, change it to AC, have 2 coils right here, and then output like 5 volts or something to turn on the LED light. And you can see it's very dim, very tiny. And the reason why is because, you know, the power here and here, like the circuits were perfectly fine, but the induction coil, there's a difference between that induction coil and this induction coil is that the one I made, I just wrapped around a water bottle and like hoped it worked, right? This induction coil, every like inch or any micrometer that it's like apart from each other really matters. So yeah, this is like inaccurate. That one's like really good, right? All right, diodes. What are diodes? Diodes are basically a switch, I guess you could say, that allows circuits to go only one direction. It's like a wall, right? You could think of the arrow, oh, my fidget toy, sorry. The arrow is the direction that it's pointing that the current can go through, and there's a wall. Meaning that if you have current going this way, it's getting hit by the wall, right? There's no key to go past it. And there's two ports, the positive and the negative port, and anode and cathode, right? And there's 2 modes. So the forward bias is when it allows current to go from one to the other. So one to the other. And if you switch it, it's called reverse bias. So the negatives on this side and the positives on this side. Again, which way does current flow from? Positive and negative, right? So positive to negative is okay. And if you switch it negative or positive to negative, right? It's trying to go this way. So it's getting hit by the wall. That's called reverse bias. And there's one more. Surprise, we talked about this a lot, but there's something called the breakdown voltage, or basically when you kill the diode, right? When you put too much voltage or too much current going the other way, that it's like a little army breaking down the wall and you finally got it. So that's when you know you destroyed the diode. Diode applications. So you can use it to protect your circuits, right? Because if you plug in the positive in the negative rail, then it can't go through, right? You could use it, or LED. Everyone knows what an LED is? Does anyone know what it stands for? Yeah, so it is a diode, right? So that's why when you plug the diode or the LED into your breadboard, you have to put it the right polarity. Oh, and when you're using diodes, it actually is, there's like a value, like you can't just go through for free. The current can't just go through for free. You have to pay a cost of around like 0.7 volts to go from one side to the other, right? Oh yeah.
Can you give us an application of forward bias and reverse bias?
Yeah, okay. Yeah, I can do that. So everyone see the board if I like right here? All right, and then pretend there's like a LED here. Okay, anyways, all right, so you are gonna put in 9 volts into, this is a 9-volt battery, right? Can everyone see? I don't know. Okay, so this is a 9-volt battery. When that means that the current is going here, it's fine, and it goes through here, right? Let's say if you're sleepy, you stayed up all night, and when you work on this project, you decide to reverse it, right? You decide to reverse it. If you did not have this diode here, this could explode. Like there are some cases where if you reverse the polarity, you can fry the system, you could make it explode. So it's very dangerous sometimes to flip the polarity. So in this case, again, current flows from positive to negative, right? And so it's going here, right? It's going here, but this is not going to let it through. And for your system to work, everything needs to go in a loop. What's up?
We didn't actually stop the LED because that's diode itself.
Well, that's true. Yeah. So if you're having the this way, yeah, that is true. But let's say if it's not a diode, if it's just a resistor, yeah, if it's just a resistor, right? Then you could still go through, but it blocks right here. And for this thing to like fully have a loop, it has to go back into the battery, right? It has to be a full loop. So yeah, reverse and forward bias. Good question. All right, so transistors. Transistors are electronic switches that turn on and off electronically. So you guys know like a push button? You're using your own finger or whatever, and you're pressing that button to turn on and off, right? But transistors, what it does, this is normally the middle one is the gate or the, what's it? The gate or the, no, collector, the base. Yeah. So a collector, or not a collector, the gate and the base, right? And what that does is when a signal gets put in like through that port, going through that port, then yeah, that pin, then it will turn on the switch or turn off the switch, depending on the type of transistor you use. So there's 2 main transistors, and this is what if you take, if you're an ECE student, you will learn this in your classes. But there's BJT, which is controlled by current, and then there is FETs, which is controlled by voltage, right? So there's 2 types of people who use transistors. There's the digital guys and then the analog guys. So the analog guys are cooler, I think. I'm biased, but basically anything like back then, everything was analog. Everything was like switches or transistors, everything was FETs, And then they use, does everyone know what like an AND gate is or an OR gate? So those are digital, basically the digital gates where when you turn binary from 1 to 0 or like, there's different rules. And all those like little chips that you guys use with the AND gates and everything, those are basically very like a lot of transistors put together to create those like type of gates, right? And then analog, how analog people would use it is they use it for amplification. Oh yeah, amplifiers. So you could put in a signal that's like 5 volts and it becomes like 10 volts, depending on how you bias the circuit. Okay, cool. So protection circuits. So going back to this right here, this is, if you didn't have this diode, it would like blow up the system or, fry it. And so basically this section is going to go over that and how other ways to implement a protection system, right? A lot of components like the Raspberry Pi actually has its own protection polarity circuit already in it, but like the Raspberry Pi has it too, but not on the GPIO pin. So the general purpose input output pins, right? So where you put like the digital pins, the other pins, those aren't protection polarity, so or reverse polarity protected, right? But the ESP32, which is like a Wi-Fi module that connects, you can connect it to your Raspberry Pi or your Arduino, that does not. So if you were to flip it accidentally, the AMS 1117, which is a voltage regulator, if it pops, then you have to replace it. Basically just fried that component, right? So we all know the diode method, which is what you kind of put earlier. This is the diode method. Not allowing current to flow in the negative way. But the bad thing about this one is that, let's say if you have this, right? This is 9 volts. If, again, earlier I explained that to go through here to here, there is like a price you have to pay, right? And it was like 0.7 volts. So when you go in here, you have to give off 0.7, and then it will be like 8.3 volts. So you're losing a little bit of voltage, right? So a better way to do that is by having a PMOS method, because it doesn't really require any voltage drop on it, right? So how PMOS work is that, so you have this circuit here, right? When you put positive, it goes through, it goes through, and it goes to the load, right? The way that this becomes, that switch closes or that switch opens, because right now it's closed and it's, constantly allowing current to go through. For it to close or open, sorry, for it to open, you have to put a voltage into this gate, right? So if I were to flip the polarity, that means that positive will be going through here and it goes in there and it opens the circuit so that it can't do the full loop, right? Drain and source. So we learned that this is gate. Drain and source is just this, right? Saturation just means that when it's saturated, it just means that it's allowing like current to go through. Okay. Any questions so far? Like, no? Oh yeah?
So the PMOS, is that like a type of transistor?
Yeah. So it's earlier I said FET, but there's a lot of FET. There's like CMOS, there's MMOS, and so those are just FETs. Yeah. Yeah, it's just a FET. And the image of like the FETs usually look like that, like the symbol. Oh wait, let me write it down. So the image of a FET is like this when you see it, right? It kind of looks like that. But for a BJT, which is the other one, it looks like this. And sometimes with a circle. Like that. Right? It's kind of different, but. All right, now we're gonna get into some of the theories and the fundamental laws. So we just learned about Ohm's law. This is, I don't know if you guys have seen this guy in the textbook or anything, but this is it George? I think it's George, but George Simon Ohms, he is a German physicist who discovered Ohm's law, right? And it states that the current, it's kind of basically this one. The current of the circuit of 2 points is going to be proportional to the voltage between 2 points and inversely proportional to the resistance, right? So that's what Ohm's law is. And Ohm's law is kind of used anywhere. Like you kind of derive any like rule based off of Ohm's law. And it's very fundamental. Like I keep like repeating. Yeah. All right. So we're gonna learn about series circuits. So what a series circuit is when the components are connected from head to toe. So you could see the switch is you know, from one end to the other, and it's still connected to the LED light, one end to the other, one end to the other, right? And the reason why I put this image right here is because any electronic component can be put into series with each other. So I wanted to show that the switch is also in series in the circuit. And for a series circuit, everything has to be in that loop. So you see the arrows, how it's going in the loop from the positive to the negative, it has to be closed together, right? And if you look at the circuit right here, what this like image GIF is showing is that in the closed loop, the current is all the same, right? And it's right there, I total. So the current going through all the resistors are all the same. However, the voltage at each point is going to be different depending on the resistor values. And how you can add these like together is just by adding R1 plus R2 plus R3. And we're going to do some practice with that too. So the opposite is parallel circuit, right? Oh, actually, so go over. So parallel circuit is when you have multiple components sharing the same node. So if you look at the top image, or even this bottom one, this voltage right here, let's say it's like 5 volts. The rail of the 5 volts is going to be the same throughout this whole line, right? So these resistors right here are sharing the same 5 volts, 5 volts, 5 volts, right? But the difference between this and series is that each current is going to be different, as you can see in the image. Each current is different through each branch. Unlike the other one where the whole thing, each of them all have the same current, right? But the voltage is all the same. And how you add, like if you want to connect all of these together into one resistor, you have to use a different equation. And it's going to be 1 over R total is equal to 1 over R1, 1 over R2, 1 over R3, et cetera, et cetera. And if you want to learn how that's derived, it's basically using Ohm's law. It's derived from Ohm's law, right? Oh, I guess a good reason. So why would you use parallel versus series? Has anyone ever like had Christmas lights and then one of them broke and then all of a sudden like all of them break or like it doesn't work anymore, right? Typically it's because one of them broke and then our Christmas lights are usually in series. So if I go back, if one of them is broken, right? You could think of the LED, like the wire in the middle, it's like cut in half, right? And that means that there's no current, it can't go to the other side. It can't have the full loop. So it kind of broke the whole entire thing. And like this one, where it shows right there, if you break an LED light, then everything still works because the current flow, the loops are still connected in a full circle, right? Any questions before I move on? Okay, now Kirchhoff's law. So Gustav Kirchhoff is the guy. He's also a German physicist. I didn't have space to put his picture here, but yeah, anyways. And what he did was he was able to find the laws of electricity for electronics, right? So his rules, he has 2. The current one, which is KCL, and then the voltage one, which is KVL. The KCL one states that the sum of the current flowing into or out of the node is equal to 0, right? Or another way to think of it is whatever goes into the node equals to whatever goes out of the node, right? And KVL states that in a closed loop, right, the sum of all the voltages across each component equals to 0. So another way I like to think of it is whatever the source voltage is equal to whatever the voltages across the components. And we'll do practice with that too. In this next section, all right, so 4.5 is because we're going to do practice. So if you guys want to, take out your paper and iPads or tablets, it's very basic. Honestly, you can probably do this in your head too. So, yeah. Okay, so we're going to try to determine the total current in this circuit, and then individual voltage at each resistor. Should we do it together, or should I give you time to do it, or 10 minutes? Okay, I guess I'll a minute. Yeah, I'll give you guys like a few minutes. I guess like a minute or two. Wait, who's actually doing it? Okay. Huh? Oh, enlarge it? How do I enlarge it? Oh, I can't make it bigger. Oh, I just X'd it out. Oh my God, whatever. Please. Oh, yeah, 3 points.
This allows us to do a workshop because, Photos gets us funding. That's why we do this.
Oh, yeah, sure. Huh? Oh, today? It's just 11:01 today. Did you want higher?
Yeah, I was hoping to come for like additional few hours. That's fine.
For which
21
21:01? Oh yeah, that's I think that's too high. I used to teach 21:01, like
Actually, told me it's like, on the workshop,
oh yeah. It's because I used to tutor for 21:01, like just that course. But this semester is way too it's too overwhelming for me, so I had to quit. I don't know how the new guy is. Yeah, there's a new guy who teaches it, but it's his first time teaching it. So. Tuesdays and Thursday you are. Yeah. There should be a form that tells you. Yeah. Oh, are you taking it right now?
Yeah.
Yeah, you could have had me as a tutor, but
That's what it is.
yeah, I'm sorry, bro.
Have it Tuesday, Thursday with like more.
Oh, then you're lucky.
Mortensen? No, a bed is my favorite.
Yes.
Yeah. But you learn a lot.
Yeah.
You learn a lot. No offense, you learn a lot compared to
everybody else.
Yeah, you learn a lot because he makes you study.
Oh, yeah, yeah.
Yeah,
This
so
is killing me. Exam, so far exam one, not bad.
yeah.
Yeah.
Good luck.
Thank you.
All right. Okay, sorry. Is everyone done? Okay. So let's solve this. I think I can just do this by my voice, but all right. So let's determine the total current, right? So let's see. One thing that we noticed is that there's no ground, right? In the image. So wherever you see the negative rail, I'm just gonna put ground. All right. So this is 9. And how do I put all these resistors together? Well, actually here, what type of circuit is this? Series, right? So that's good. It's series. So how would I solve for all the currents? Right? What does series circuit tell you that for the current at least? Yeah, so when I say total current, it's the same throughout the whole system, right? So how do we do that? So what we're gonna do is we're gonna combine all the resistors together, and how do we do that? Add them, right? So 3, 10, and 5. What is that? 18? 18K ohms, and then you have Ohm's law, which is V equals IR, right? So when I put this, it's gonna be like this. So this is the resistor total, right? So this is R total. And and this is 18K ohms and then 9 volt. So Ohm's law states that V equals IR, so we're looking for I total, right? So V total over R total equals to I total 9 volts over 18K. So, and then did you guys get 0.5 mega amps? Milliamps? Right, so if the if the total current is the same, then how do we find the individual like voltages, huh?
Oh, I would.
You could use voltage divider. You could also use, since everything's in series, you can just like multiply, use Ohm's law, right? Since we're focusing on Ohm's law, you can just do VR1 equals to I, right? Because the current going through R1 is the same, so 0.5 milliamps times 3K ohms, right? And then you do the same thing, R2, 0.5 milliamps times 10K ohms, VR3 equals to 0.5 milliamps, 5K ohms, right? And here is the answer. Oh, here is the answer, right? So everyone got those values, right? Okay. So now we're gonna take a little break. So this is LT Spice, and how I'm gonna simulate. Wait, what do you guys use to simulate your circuits? Okay.
It's I think for 2300.
Oh,
I use Spice or like OrCAD for
Mhm.
2300.
Okay. Yeah. Some professors use LT Spice because it's free. I used it at work too, because I guess the company wanted to save money. I don't know. But so what you're gonna do is you're gonna open a new schematic. Oh, I already did. It opens a new schematic, and then you're gonna go to here, components, right? And then you can put R. No, there's the resistor right here. Sorry. Right? And then click R to rotate. No, control R to rotate. Oh shit, I should have done like, hold on. So rotate this, rotate that. Oh my God, this is so hard without a mouse. Okay, and here. And then you could just go to components, find voltage, right? And then click on the wire and just connect it directly. Right? Oh no. Hold on. And only LT Spice allows you, like, you know how I'm not going directly at each, only LT Spice allows you to do that. So other spices, other component, other like things don't allow you to do that. So to change the value, we have 9 volts. You just right click on the component. DC value is 9 volts. 9 volts. And then same thing, resistor value, what was it? 3K? We can just put 3K over here. I think it was 10K. And then over here it is 5K, right? And then to run it, you just click run, stop time. I mean, this doesn't really matter. Or I could do transient, means that from time 0 to something, or time, time. We're gonna do from 0 to, oh wait, time start saving data is 0. Wait, time to start saving data, and then, oh, stop time, sorry. Let's say 5 milliseconds. And then time step, I can just say 1 millisecond. Right? Oh, now what does it say? The circuit does not have a ground. right? So this is what I was saying earlier. You can't simulate without ground. So I'm just gonna put ground here. Again, I put the ground where the 0 is, or the negative. And then I should run it and it should work. Oh, wow. Okay, hold on. So this is where the time is, but we don't really need that. We can just put the probe right here. So if I put the reference marker to here. Oh, it's gonna give me a negative, I think. Place data. This point is going from the reference point. So earlier I explained to you guys like the node voltages. That's what this is. It's not like if you want to find the point, these are here. I don't know. PSpice does this a little better. But right. So what we can assume here, do you guys remember what the one of the rules were? KVL? KVL states that the voltage across the resistors or in that loop has to be equals to the source, right? So you could see 7.5 and 2.5 equals to 9. That's why you can do that. And then when you do it on here, right? If you connect all the, like add them all up, then it does equal to 9, right? Any questions? No? Oh, wait, me also. If you put your probe over a resistor or like a resistor, it tells you the current of it. Okay, and hold on, I need to run it again. So we have, oh, it's negative though. Why is it negative? I don't know. But it's supposed to be 0.5. I don't know why it's negative. It's just the polarity, right? And then if I put a reference here and here, it's gonna give me negative because I put the negative black one on to the positive rail, right? So yeah, you can like test it out, whatever. Okay, next one. Same kind of idea. Just by looking at this, you should be able to solve it, hopefully. If not, I'll give you a few minutes. You guys need more time? No? Okay. So what type of circuit is this? Yeah, so it's a parallel one. So we first identify, and that means that we can state that at node 1, 2, 3, and 4, it's all the same, right? So if it's 9 volts at node 1, that means that it has to be 9 volts at node 2, 9 volts at node 3, 9 volts at node 4, right? So technically, if it's asking to determine all the individual voltages at each resistor, it's gonna be the same, right? So VR1, VR2, VR3 is all 9 volts, theoretically, right? So the important part now is finding the currents. So how do we do that? Any ideas? Anything? The lower one? This one? What about it?
The different variable that can be around that with the total resistance, right?
If you put it, are you trying to do,
So your total resistance gonna be less than 1 kilo.
yeah, because it's 1/.
And then you divide 9, is that, so it's around less than 9 meters.
So that's for the total current, right? So if what she was saying was that if you combine all the resistors together, then and then you find the current, then you would find the current of I total, or I guess this one, I total 9 volts, and this is R total. This one is this. Right, so if you find the total, you add it all up and you find the total current, then you would find the current at this point right here. Right? But that's not the individual current at each resistor. So you found one part of it, right? Which is in, what's up?
You could use that to check like later on to calculate it.
Mm-hmm, yeah, but you still need to find all the other currents first, right?
Well,
Yeah,
I was gonna say voltage across all of them is the same. You
Mhm.
multiply them times the resistance.
exactly. So you're still using Ohm's law. And since you know that the voltage here is 9 volts, this is 9 volts, this is 9 volts, and this is 9 volts, right? Each one has its own current, right? So all you have to do is using Ohm's law, V equals IR. And you're trying to find trying to find V, no, R. I mean I. So you're trying to find I, right? So then that would mean I equals V over R. Since you're given these two, then you can just find IR1 using 9 volts over 10K, and then the other two too, right? So here are the answers. Oh, there you go. Since they're all the same, they're in parallel, the 9 volts. And then you're finding each for Ohm's law, and those are the solution over there. So if you just do the math, that's what you get, right? Yes.
How did you do the math?
I use Ohm's law. All right. And then if I go, any questions before I simulate this? No? All right. So going back to this one, where's my right? I'm gonna actually I should not have done that, but okay, let me go back. Let me just delete some stuff.
I've heard you on this. Yeah. That is then not part of the speaker. Yes, I think we measure it, but you wanna. And then put all of that. Or you just ask more. Yeah. You're good, but like, I just. You're good. Okay. We're not doing anything. Yeah. Cool. We're gonna. Yeah. It's just saying that. Okay. Put it out. It's best. Down left art. I think it's. I think I goes. What is it like? You can't get any. We don't need. That's
All right, so I guess I simulated this, and you could see that it looks exactly like what I wrote, right? 9 volts on top, 9 volts here. And now we're gonna test out the currents, right? If I run it, I don't know why this is going up. But anyways, what is this? We can just click on here. Oh, here. Where- And it'll tell us the value. So this is 9 milliamps. 0.9 milliamps, or is, no, wait. Is that, well, 0.9 milliamps, right? So we go here, that is 4.5 milliamps. And then over here, oh, there it goes. 7 milliamps. Wait, 7 or 9 milliamps. I'm dyslexic. Yes?
Why would like your first two values?
I don't know.
It's because the way you're measuring it.
Going
always-
backwards.
Yeah, it's just current, it's just.
Yeah, I don't know why it's going down. I know, like, when I was doing some of my projects and they simulated, my professor said that if it's negative, you just switch the signs if you know that it's the other way. Yeah, I don't know why it's going up.
It's spices.
Yeah,
Or
yeah, so sometimes I don't know why. It's doing that. I'm also like kind of surprised. I don't think it does this on PSpice though. So I think it's just because for LT Spice, you can't like, normally you would have to break it to measure it. And then you could put like the positive and negative, but I don't know why it's doing this. Do you have a question?
Yeah, what would you recommend is like the best resource for to learn these books?
So the one you use normally at work, like what they look for is PSpice. You can do LT Spice, but it's not that like good. So PSpice is one I recommend, and you use it for the higher division classes if you're in EE. So you use PSpice. Yeah, that is not capped.
Well, what?
Well, at least if you have like Olsen, then you use PSpice, but LT Spice is free. Yeah.
How do you like go about learning the software? Like how do you use it?
How did I learn it?
Like, yeah, like my teacher like teaches how to use Spike, he just wants me to use it.
Mhm.
So like how do I learn how to?
Yeah, YouTube.
Yeah.
Yeah. YouTube until you get a good professor. So my professor, Professor Olsen, I don't know if you guys know her. She teaches normally the higher division, but she put like a PowerPoint together of how to use PSpice. Like it was like 10 to like 20 pages of how to use PSpice, like step by step too. What's up?
If you don't, I mean,
What would you say?
what do you use it mainly for?
How do you use an industry manual?
Oh, so when I was, hopefully this is not like I can say this, but basically what I used at work was, it's not this simple, but I had to simulate like an op amp and I had to have the simulation, like the curves and everything of the amplifier. So, and then what they needed me to do was their slopes wasn't matching up to their theoretical or they're measured. So I had to go in and kind of tweak the resistors and the capacitor values. And by changing those, I'm changing basically where the best like frequency is at. Because what I do at work, I do a lot of like RF. So I'm changing basically how good it is at each frequency. It's just tuning. What I did was just tuning the circuit. But I had to simulate it and that's what they wanted. So yeah, I use LT Spice. Yeah. Did you use anything at work?
Oh, me?
Yeah.
No, we don't really use a lot of the stuff we use, not more just looking at one line diagrams, so a lot of power stuff.
Yeah.
None of this small shit.
Small level stuff. Yeah. Yeah, I went into like the board. I think he saw like the overall system, but
Go to where she's going, it's where you make all the money,
no.
sell your soul.
But where you go, I worked at Northrop, so yeah.
So sell your soul.
But he worked in like the power for the government.
I did like, yeah, you mostly, like, not really distribution, kind of distribution for the Army Corps dams. Huh?
Helpful things.
No, our dams are literally, air, so we have 2 active dams in California, in Southern California, so.
Yeah.
What is the company you work for?
Northrop Grumman. Northrop Grumman? Never heard of it? I think that Pomona, like all the engineers, at least the EE or CE, they end up going to defense. And so defense is like Raytheon, Northrop, Lockheed. Is SpaceX one? No. NASA? Is NASA defense?
NASA's not hiring right now.
Oh, yeah.
They're out of money.
Well, yeah,
No, for real, they're actually out of money.
yeah. It's just the ecosystem, not ecosystem, the economy is just really bad right now.
One from Space, from Karwal that just dropped it off.
Yeah, from NASA. Yeah, they laid off a lot. But it's basically working on stuff that go into the army, the military. So
Well, I missed it.
yeah, missiles, bombing.
This is the end goal anyways, to make a bunch of.
Yeah. Yeah. So like, yeah. Huh? So what I did was I was an RF tester.
Yeah.
I'm going, well, I have it like going back, but yeah. What's up? Yeah. Is anyone here interested in RF?
That missiles.
No.
Anything.
Anything, just shooting signals at you. RF is basically radio frequency, so like antennas and waves. Yeah.
Do you do like programming as well for the signals? Or is that all
She doesn't.
I am the worst person at coding. So, well, yeah, I don't really code, but a lot of people they do code to like test your thing, but thankfully they already coded it for me. All I had to do was like, measure everything and then press buttons. So, yeah.
That's a lot of questions because I talk to my professors sometimes after talks about like all the different fields. And it's so broad, the things you can get into. But he was like, I feel like you have to be a little proficient in code, like in a little bit of everything in coding. And I was like, I don't like it. Like, well, you want a job.
Yeah. Would you say I'm like bad at coding?
Yes.
Brian, the one with the hat is, or I guess they're both wearing hats. The front one, he was my lab partner for like a few classes. So
He carries.
he's the CE. I just EE. But you think my coding's okay? You can be honest. Oh yeah, he says 10 out of 10. No, but honestly, I think my coding skills is probably like a 7. So I'm not that good, but I only know one language, which is MATLAB, Arduino, and C. So yeah, but they're all kind of the same languages though. Oh no? Okay, well, I don't know like Python, which I probably should. I don't know.
Yeah, that's leave it.
Yeah, but yeah. So you guys, wait, the only reason why I asked if you guys like RF is because like I was debating if I want to have like an RF workshop, like where you guys learn about like antennas and like.
Yeah.
Do you
Yes, Maggie, do it.
Oh my god. Well, I'm not
Can you do it?
Yeah.
Do it on Monday.
On a Monday? Why Monday?
Yeah, do it on Monday.
So yeah. Should we continue? There was one more circuit, but oh, there's another one. Should we do it or?
Yeah, do it, Maggie.
Oh my goodness. Okay. This last one is from the King book.
Wait, should let Brian do it on the floor. Walk him through it.
Oh, does anyone want to go do it?
Brian. He's literally making that.
Wait, did you want to do it?
I could.
Yeah, you can do it.
No, I'm shy though. What if I'm wrong?
Yeah, we'll help you.
You cannot mess us up.
You make those in parallel on the right, and then you make them in series, and then you find a total current. And then
I mean, you don't need to find, you could just make those parallel, do a voltage divider, and then.
We haven't learned voltage divider yet.
Oh,
in series.
yeah, you went series.
All right, so what was the first step?
So R2 and R3, you have to do an REQ equation.
R2 and
But
R3.
we don't seem to have a number for the second resistance.
Uh-huh.
No, that's not even a question. Determine the voltage resistant value of R2.
So you're trying to find this voltage?
Yeah.
The resistor value of this, and the current I1.
Is it given?
Huh?
Determine the voltage in this invalid or and current, the current's given, okay.
Mm-hmm.
So you do KCL with I2 and I3, and that's what you have at I1,
Mm-hmm.
and then you get the voltage there. And
Oh,
then,
let me stop you real quick.
Yeah.
KCL is basically at that node where normally in like the King book, if you see a dot, that's a node. So whatever current is going in is equal to the current going out, right? So we have I1 is going into the node, and then I2 and 3 is going out of the node. So what he was saying is if you're given you're giving I2 and I3, you can find I1 by doing I1 equals to I2 plus I3, right? Okay, continue. Sorry. Oh, yes, sorry.
I remember doing, this is like one of the problems in the homework that we have.
Oh, really?
Yeah, but the thing is that I was confused because like for this one, since you know how like I1 is like, it's the same thing, like coming out is the same thing coming in.
Mm-hmm.
So, like using KVL and also,
KVL?
also Ohm's law,
Uh-huh. KCL?
yeah. I got like a different answer using both of those, like KCL and Ohm's law, like starting from like, so like you know, like to find I1, it's like starting from the top, it's like 6 volts over the R1 right there.
Mhm.
And that should be your I1, right?
No, that is not because
there's a total.
no, just kidding. Because that I1 is only there's a node in the way. So the voltage between that point right there, that corner point, versus the node, like between that is not 6 volts. So you're saying that the voltage across R1 is 6 volts, but it's not. It's a different value. I haven't measured it yet, but
Oh, sorry, so then the current would be like the equivalence, like it's the voltage over the equivalence of the 2 resistors in parallel.
Plus the.
Yeah.
Yeah,
yes.
that would be the total current.
Yeah, at that one. So if you just did 6 divided by 6 divided, wait. Yeah, 6 divided by R, that's not gonna give you I1. Yeah.
So I just go and solve.
Yeah, you can go. Solve. Yes.
Can you show them a Thevenin equivalent for this one?
A Thevenin equivalent? Wait, Thevenin equivalent, you have to have the output. Thevenin equivalent is basically just another rule that I just didn't want to go into because it's more difficult. But you use it a lot in 2101 and 11. But that was a good question.
And you use a lot of 2200.
Thevenin?
Yeah.
Oh yeah, open circuit, yeah.
Diodes. You should take Andrew Pagnon and give a chance. Take Pagnon. Whenever you have an opportunity, take Andrew Pagnon.
I have to stay
For 2200, I suggest Miskus. Wait, what was his name?
Andrew
Miskus?
Pagnon.
No, Miskus.
Oh yeah, Mr.
For 2200. Yeah.
Doesn't he does
I think
32, doesn't he?
Oh, is it 32?
Yeah.
It's either 22 or
Don't
32.
I will say that.
It's recorded. No, I'm kidding.
What did you say?
Miskus?
Take everyone. Everyone's good.
No.
Yeah, everyone's good, uh-huh.
Everyone's good.
I'll last.
Everyone's good.
Oh, let's see.
So you know.
Then you were able to solve. Like that's the way for just for him, that's a book we forgot jelly.
Maggie, do you lower these?
No, dude, I don't
No,
know.
when they like go.
I'd rather use that one.
Yeah.
You know what?
And then to get your final one, I like.
Uh-huh.
You want just your read order and go.
Yeah, or you can do it the way it's
Oh, yeah, for at least, yeah. Yeah, so your I1 something that is equal to I2 in the year.
There's alright, so how would you solve for B?
Well, you can decide it's to struggle across this first.
Oh, the easier one would be the way
You subtract.
Oh,
Is it?
if you find the current. You get the current.
You can just put it.
Right, so I'm gonna try to show you like the most optimal. So I'm gonna try to show you the most optimal way just by looking at the circuit. Like you can just solve.
Yeah.
So what you're going to do to find, so what he said earlier was that you find, like you put these together and then you find the current here and then you solve, you multiply here. But this is a parallel circuit, right here, only right here. So that states that if that node is equal to this node, right? And we're given I3 and this resistor, right? So what I'm gonna do, wait, sorry. Oh, what I'm gonna do, we're gonna start from the right. Normally you just look from the right to left, right? I'm just gonna find the voltage at this point because it's equal to the voltage here, right? That's why the VO is in the middle right here. If you like, just like a rule of thumb, like a tip, if you see the voltage over here, then it's gonna normally be that voltage here. But you see if it's in the middle, it's probably both, right? So by multiplying R3 with I3, you get VO because it's that point is similar to that point, right? So how would I find R2? So I just had the voltage on the top, right? Yeah. So you're given I2 and you have the voltage across R2 now. So you just use Ohm's law. Yeah. VO over I2 and then you get R2. Right? So this problem doesn't really do anything with combining it. So that's why I said this is like the most optimal way, because you don't need to combine anything, right? You can just really just look at it and see. But you can do it that way too. Honestly, there's no wrong way to solve circuits. It's just like your time.
I was just forgetting the givens.
It's okay. No worries, no worries. Yeah. Oh, yeah, sorry. And then I just put this as last. So those are the values. That's the answer. Yeah. The only thing that sucks is that I don't know how to simulate this if you don't have a resistor value. Yeah, I don't know how to simulate if you don't have a resistor. So I don't. But yeah, thanks for solving it. I mean, you did good. Are you in 1101 right now?
Yeah.
Enjoy that shit.
Yeah.
Is Ollie gone? Yeah.
Ollie's teaching it?
Yeah. He's
11 or what?
I'm so sorry for you.
Yeah.
My friend is not okay. I had some.
No, it's not about-
average is like 5%. I mean,
The best.
We had Gonzalez. So
Shut up.
we had Gonzalez.
Dude,
We got Gonzalez?
Yeah. Oh, Zeki?
Dude, that he's the goat, bro.
He's impossible. Actually, he's like, you guys are
Good.
He's extremely good, but he's super.
No. He's gonna have.
Yeah, that's pretty good.
Yeah, you by yourself film them, an item for the one time, and basically getting great angle labs.
I know.
They were all done.
Are you done, Maggie?
Well, I have 2 more sections, but honestly, I don't know. You guys want to go? I'm just showing some like application.
But you have to.
Cool circuits.
Yeah.
Let's see these cool circuits.
Okay.
Yeah.
Oh wait.
I was looking for office hours. Yeah, we did this bomb like a few times I wasn't even
Huh?
there, but.
Is this classified?
No.
Yeah.
All right. So I'm gonna show you guys. I guess 2 more sections, but one is design, which kind of takes forever. I'm gonna just show you guys the circuits. So these are some cool circuits that I thought were pretty cool when I was like 1101 and 2101. So this is an LM7805, and this is a voltage regulator, which regulates, you input like 7 to 35 volts, and the output will always be 5 volts. And you just need some capacitors to store the energy and stuff like that when it discharges. And so this is very used. It looks like a MOSFET. Funny story, I had a CE come up to me, and no hate, but he was like, oh my God, for my 3D printer, I had to buy a MOSFET, and I put it in, and like it worked perfectly. And I was like, you had to, because normally when you like fix stuff, you don't really, just buy a what's it called, a MOSFET, and just connect it, right?
You didn't remember that?
Huh?
You didn't remember
Just
that?
ran.
3D printer with a MOSFET?
Yeah. Yeah, and then I looked at it, I was like, what was it? And then he showed it to me. It was this thing. It was just a voltage regulator. And a voltage regulator, how I explained, is like a bunch that's inside that. So it's a bunch of like transistors that I keep telling you guys. Those are BJTs. And so yeah, don't get confused. That's not a MOSFET. It's actually, they just come in the form of like, it looks like a MOSFET, right? And then this is basically another voltage regulator, but you can adjust it. You can adjust the output depending on the volt. This is a voltage divider right here. You can find the values. It's changing by the resistors. You can get different outputs, but each chip has its own like limit for the amount of input current you can put in. So it's just right there. So a full bridge rectifier is switching from AC to DC. And AC circuit or AC is basically like sine waves. So what I did, or what this circuit says, is that you have an input that it's a AC input, and the output using this full bridge rectifier is gonna make like the wave. Just draw it. So the wave, it's gonna go like, a sine wave. And then after the diodes, it's gonna be like something like, it's like waves like that or something. And then with the capacitors, you're using it to filter it out. So then after the capacitor, the way it discharges, it becomes like, but it's like that. And if you have like a straight enough line, you put it into the voltage regulator, and it can output a specific value. So I think you build this in 2200.
I'm taking
Full bridge.
Yeah, you take it. Also, you have to know what this is for interviews. I got asked this. A half bridge and a full bridge rectifier. Okay, the last one I thought was pretty cool. This is a FM radio amplifier. So an antenna, what is an antenna? Does anyone know?
The stick.
It's not a stick. It's a wire. So you can, so what he was saying was he was talking about the black stick that, that looks like an antenna, but inside that like coating is just a wire, right? So any wire, you can use a paper clip as an antenna, and you just coil it up, stuff like that. And so the antenna goes into, and when everything is in the air, everything is waves, right? So it's just propagating through the wave or through the air. And when you have that specific frequency that you want, it goes into the antenna. And this is a tuner circuit. So by changing the values, you can actually change the frequency of the input that you want. So earlier when you asked me what I did, I was basically tuning the circuit. So that's what I was doing. I was tuning the values, so then the specific frequency goes through my circuit, right? And then when you take communications, you will learn that there's something called an envelope detector. So you have a wave like this, and up here, this is like the envelope, right? That's like the envelope, the cover. So it's gonna take that, and it's going to basically make it like, it's gonna I don't know how to explain it, but it just takes the signal in the real world and it takes out the envelope. Okay, that's a bad, let me draw it. So FM is, not to go into too much detail. This is like an FM signal right here. And the way it works is that you have you're mixing two signals. You have the like data signal, which is this top one. And then you have a carrier signal, which is like a really high frequency that carries the signal, like the data signal, right? And so when it goes into the antenna, this is what it sees, right? And it can't read this because this is two different signals. You have the carrier and the envelope. So the detector is basically just gonna take this top part, extract it from this whole signal, and then input it into the amplifier. Right? So now it goes from the antenna, this is like what the antenna sees, and then it goes into like a sine wave and it amplifies it to like a bigger sine wave and outputs your data like loudly, right? So yeah. I wanted to build this for the workshop, but that's
So
pretty
you
good.
said that the
Mhm.
carrier signal is like a high frequency, right? So
Mhm.
are normally the data signal and the carrier signal different frequencies?
Yeah, if they're the same frequency, then you get mismatch, like you get interference. And the reason why you see that this is like really fast is fast frequency is like really, really quick. It depends, like tau or 1/, frequency equals 1/t. So it's really fast compared to your signal one. If it's the same, then it's gonna be some interference, like the same frequency. So you want this one to be a lot higher than this one. So that's why you can see it's a lot slower compared to this really fast signal. And this class you will learn that, like this where you learn this is communication systems. And I think only EEs have to take it. So
Comms?
yeah.
Oh.
Yeah, only EEs have to take it. But it's a cool class. So you can take it as an elective for your CE.
It's fun. Watch that. Oh no, I forgot. It's on the left.
Yeah. So that was pretty. Yeah, exactly. You have to do everything by hand though. Yeah. There's a lot of math involved in this. So. Dr. Yu. Yeah. And so I guess that's the cool signal.
Oh.
This is a challenge, but you guys could just do this on your own time. It's just using the simulation, just copying the circuits, but I think we already simulated it, so I don't think we really need to do it. But yeah, if you guys have any questions, yes?
What was the question you were talking about that?
This one?
Yeah.
Communication systems, which is 4709. Bye. Yeah, 4709. Thanks for coming. If you guys have any questions, you can just come and ask up here if you guys want. So, thanks for coming, everyone.
Oh, inside, but kind of. Yeah. Direct.